Welcome back. Now, we're slowly putting together the pieces of the puzzle of the VIT architecture. And we've broken it down into three main pieces, being Figure 1, the 4 equations, and Table 1 and Table 3. So in the last video, we broke down Figure 1 into inputs, outputs, layers, and blocks. The next thing we're going to do is move towards breaking down the 4 equations. Now, if you are not familiar with mathematical notation, not to worry, it is just like another language like programming to learn. But what each of these equations defines is what's happening behind the scenes of each of these colored blocks. So I want to show you a trick before we jump into each of these of how I deal with mathematical notation and replicating papers in general. So if we come into the VIT paper, we've got section 3 method. Now 3.1 breaks down what goes on behind each of the equations. So we have an overview of the model is in Figure 1, which is what we saw before. This is Figure 1. And then if we keep reading through here, I'm not going to read it verbatim, this will be your extra curriculum. But if we start off with just an example, the standard transformer receives as an input a 1D, one-dimensional, sequence of token embeddings. So this is the sequence here. We've turned an image into patches and then into a sequence of patches. We're going to see how this works with code later on. So to handle with 2D images, we reshape the image. X is an element of a real number with dimension h times w times c. Where have we seen those letters before? That's height times width times color channels. And the reason why I know how to sort of read these, and in fact, there's a lot of mathematical symbols I don't know how to read, but I've just had a lot of practice reading symbols like this. And do you remember what the small non-capital letter means? It's often a vector. So we have an input image, but in this case, it's kind of confusing. So X is just the input in this case. And a capital is often a matrix. But again, the nomenclature here is a little bit confusing. But let's just say we have an input image X, which is an element of a real number. So all the numbers that comprise X are real, of the dimension height times width times color channels. That's just our input image. And then we convert it into a sequence of flattened 2D patches. So we have flattened patches here. We convert the image into patches. We'll see this with code later on. I sound like a broken record, just reiterating that we're going to turn this into code. And so then XP, P is for patch, is an element of a real number of shape N. We don't know what N is just yet. We haven't read it yet. Times P, I believe P might be patch size, squared because the patches are squares. So it could be patch size here, squared, and then the dot product of the color channel. So we can write some code later on to figure out these input and output shapes by hand. In fact, that's actually going to be a really good piece of practice. So if we keep reading here, where HW is the resolution of the original image, so that might be height and width is 224 pixels. C is the number of channels, so color channels. PP is the resolution of each image patch, so the patches are in squares. So patch width and patch height. And I'm sorry for jumping around a little bit, but we're trying to explain some non-linear information, as in this patch is related to this text that's expressed in a linear format. So it's a little bit hard to jump around, but we'll see some visualizations later on. Is the resolution of each image patch. And N, so N is this N up here, equals height width divided by patch squared. Okay, so that's how we can work out how many patches are in an image. So the number of patches, which also serves as the effective input sequence length for the transformer. So this will be, N will be how many patches we have here, the length of this sequence, which is the input into our transformer encoder. So let's keep going. We'll just finish this paragraph and I'll let you read the other 2 or 3 as extensions. The transformer uses constant latent vector size D. So this is going to be latent vector size, might be an embedding vector, for example, through all of its layers. So we flatten the patches and map to D dimensions with a trainable linear projection. So trainable linear projection here means embedding or learnable embedding, which is, if we look up here, linear projection of flattened patches. So we split the image into patches, turn those patches into a sequence, so flatten them, and then embed those patches into a linear projection of flattened patches, and that's going to be our input into our transformer encoder. But of course, we add a position embedding and a class token embedding. We're going to see those later on. So one more sentence here. We'll just reread this. So we keep the latent vector size D through all of the layers. So we flatten the patches and map to D dimensions with a trainable linear projection. That's equation 1. See how this paragraph is explaining what's going on in equation 1. We're going to look at each of these individually over the upcoming videos. And then we refer to the output of this projection as the patch embeddings. Okay, so equation 1 deals with the patch embeddings. So if you want to read on with these 3 paragraphs here, these are what explain equation 2, equation 3, and equation 4. So if we see here, the transformer encoder, Vaswani et al. 2017, so that's the original Attention's All You Need paper, consists of alternating layers of multi-head self-attention, MSA, so see Appendix A for a definition, and MLP blocks. So we've got MSA, multi-self-attention or multi-head self-attention, and MLP. So that's equation 2 and 3. And then if we keep going, layer norm is applied before every block and residual connections after every block. So there's a lot of information to take in here, but I'd encourage you to read back through section 3.1. What I like to do is when I'm replicating papers is I like to get this text into where I'm working. So, what you might also see is I've just replaced, in the previous video, we turned these images into markdown image tags. I've turned them into HTML image tags so I can adjust the width and add alts here, so alt comments. That way screen readers can read out what's going on with the image. So now let's copy in section 3.1. This is my trick. If we just copy this, it doesn't format too well. Because see how there's a lot of symbols and whatnot? Yeah, look at that. We've got all that extra stuff. If we bring that back into here, look, that's just a big blob of text. We don't really know what's going on there. So let's delete this. One of my favorite tools is MathPix. And like all good cooking shows, here's some text I've prepared earlier. So if you read through all of this, this is all information from the VIT paper. So I've got VIT paper replicating. You can create one here. I'm not going to do a complete demo of mathpix.com. I'm just going to show you what we're after. So this is just an editable notebook here. So if I type in something, yo, what's happening? It's going to appear on the right there. But I'm going to delete all this text just to give you a demo. And this is what I like to do. This is a beautiful tool. So if 3.1 is explaining the 4 equations that we'd like to break down, I might want to take a screenshot here. So I'm going to take a screenshot of what's going on. That's going to appear down over here because I'm using a Mac. And then I'm just going to drag this over. Looks like it's working. We'll just let this load. And oh my goodness, look at that magic. So you see here how we've got all these little dollar signs and all these math RM times, H times, math BF. I think that means math bold font. You can correct me if I'm wrong. But this is, I never really learned how to write LaTeX. This is what this is, LaTeX. So if we look this up, LaTeX. And that's how a lot of papers are written. Okay, so don't search LaTeX in images. I mean LaTeX as a document preparation system. So this is a way to write the formatted text as you see here. So now I've copied this over into mathpix.com and I can just copy this exactly how it is because Colab notebooks support LaTeX. And I might just break this into another cell, table 1. Okay, Command M minus in Google Colab to break another cell. And I'll break this into another cell, Command M minus. Beautiful. So this is what it describes equation 1. I'll just put this as section 3.1 describes the various equations. So we have a description of equation 1 here. We're going to go through these one by one in a second. Then we have a description here of equation 2, or equation 4 actually. Yeah, see how it describes? Things are kind of out of order here. And then this is equation 2 and 3. And this is also a little bit of equation 1 here. So that's my trick for this video. We've read about equation 1. We haven't replicated it just yet, we've just read about it. And this is important. It's going to take you a few times, and it took me a few times to really realize what was going on, what's happening here. So for your extra curriculum for this video is to read through section 3.1 again from end to end, including the equations here. And don't worry too much if you're not familiar with the math symbols. Just read through it once or twice. And then if you want to, you can try out mathpicks.com. You can get all of the text. This is going to use OCR behind the scenes and computer vision to break it into editable text so that we can copy that into our notebook. And we're going to come back over the next few videos and go through each one of these equations one by one. So I'll see you there.